So what you just accomplished on those pages, we're going to do formally in our notes. So you're going to see it again. We're going to do a little bit of starting to look at why the definite integral or the Riemann integral is what it is. So our first thing is we're going to just sort of think a little bit, do some notes on that. Nothing to write down. Just think about what's happening. So we want to find an area under a curve from A to B. And we have all these rectangles. And each of these rectangles has a little area. There's always a rectangle that's below and always a rectangle that's above. So if we look at a tiny little section, there would be a height of y, a length of x, and there'd be, for the maximum height would be however much you changed in y, depending on how much you changed in your x. And that would be your little bit of area that you would get. Well, if we do some algebra with this, it would make sense that the area of the small rectangle is less than the actual area, is less than the area of the big rectangle. We create an inequality. And since dx is some little number, we divide everything by dx and get this expression. In the middle, where this delta change in area and change in x, those are two things that change as you make things smaller, it starts to look like a derivative. In fact, if change in area over change in x represents an average rate of change of the area, if that goes to 0, that would represent an instantaneous change in area. And an instantaneous change in area would be your derivative. So as the dx goes to 0, this becomes the derivative. But does it make sense if we look at this? If you make this go to 0, can you see that this goes down as you do that, and it goes to 0 as well? So if we kept making our rectangle smaller and smaller and smaller, eventually we would just get y on either side. However, in the middle, we have the derivative. And if the derivative happens to be between y and y, then the derivative, by the squeeze theorem, is just equal. Oops. It's just equal to y. And then if you integrate both sides, here we could do our antiderivative. If integral of dA dx, that's just a. And it says, therefore, the area is all of y. Now, here it's not quite right, but it's sort of an idea saying if this equation would give us the area from the origin up to any value, then if you wanted to find two values, you could just take the area of the higher one minus the area of the smaller one and get them out. We'll look at some more videos of this to really explain it. But this is just an idea that your area is the definite integral of some function. And we've done, this is the Riemann sums, where you add up all of these rectangles. And as your rectangles' lengths become smaller and smaller, as you get more and more rectangles, it's going to become the exact value. So this is the idea that we're getting at. But we're going to do a few more Riemann sums first. Okay? So we can always approximate our actual area with our Riemann sums. Or do you feel like you're getting good at Riemann sums? Can we skip these? Do you want to write them down? Do you really want to write them down? Yes? Okay. So if you wanted to find the area of x minus 2 squared from 2 to 10, and you had 4 equal intervals, we could write down what our intervals are. You would go from 2 to 4, 4 to 6, 6 to 8, 8 to 10, which means your change in x is 2 every single time. Here's a picture of what's happening. And notice we got the little arrows always on the left ones. Here are those left rectangles. Obviously, because the function is increasing, we would have an underestimate. And each of those rectangles, you just need to do base times height. The base in all of them is 2. That's your change in x. You figure out all of your values when you plug them in. Then we get our underestimate to be 112. Yes. Can you zoom in? I can zoom in. Start the video. Okay, so the second one is 240. And I have a little YouTube video that I want to show you.
We've seen how the sum of areas of narrow rectangular slices of the region under the function curve gives us an estimate of the area of that region. If we increase the number of rectangles toward infinity, their widths approach 0, and the sum of their areas approaches the exact value of the area under the curve. This is illustrated in the animation you see at left. So the question is, can we write the definite integral as an infinite sum to allow an actual computation of the exact area? The answer, of course, is yes, and this video will explore how to write such a sum in sigma notation. We start by considering the limit definition of the definite integral, which is the limit of the Riemann sum. Inside the sigma operator, we have isolated one rectangle at some value of x. Its height is the function value at that x value. Its width is the width of one slice of the region. Multiplying the height times width gives us the area of that rectangle. The sigma operator adds all the rectangles from the first to the nth or last rectangle. We carry out this sum using larger and larger values of n, such that the value of n approaches infinity. This sum will thus converge to the exact area. But the sigma notation we just saw does not directly give us an expression we can use to calculate the area. We would like to find an expression that uses the interval endpoint values a and b, the function operation, and the index counter k, counting from 1 up to n. We start by noting that there are n rectangles, each of width delta x. This width is 1/nth of the distance between a and b, which is found as b minus a over n. Now we can find an expression for each x value corresponding to the position of the vertical side or edge of each rectangle. Since these x values are in multiples of delta x, starting at x equals a, we can say that each x value is a plus some number times delta x. So the first edge is at a plus 1 delta x. The second is at a plus 2 delta x's. The third is at a plus 3 delta x's. And the fourth is at a plus 4 delta x's. As n increases, we simply create more of these x values in the same way. The kth rectangle's edge is at a plus k times delta x. Now we can see that the height of each rectangle is simply the function value at each of those x values. For example, the height of the third rectangle is f of a plus 3 times delta x, since a plus 3 times delta x is the x value at its edge. But remember that we have an expression to directly calculate delta x, which is b minus a over n. So rectangle number k has an area of its height, f of a plus k times b minus a over n, times its width, b minus a over n. To get the total area,
All right, now that we've been doing things for a while, when you see this, it's not as overwhelming as it once was. Is it getting to that point? Because if I just showed you this video once and said, all right, are you guys good to go? The answer most likely would be, we're very lost. But now that we've been doing this enough, hopefully we're getting better at it, and we're about to just do some questions that work with this.
we will just add all of the rectangle's areas from rectangle number 1 to rectangle n. Here's the original limit of the Riemann sum, and here's its equivalent in a more computation-friendly form. We simply replace x sub k
So much
with
friendlier.
a plus k times delta x, and we replace delta x with b minus a over n. Let's look at a couple of examples to see how simple this really is. Let's start with the definite integral of 6x squared from 1 to 8. We write the limit expression replacing x with a plus delta x times k, and then further replacing delta x with b minus a over n. Notice how the constant 6 stays put. We only need to change the x's, and we maintain whatever operations that the function f directs. Here is the simplified form of the sum. Another example is the definite integral of the natural log of x from 2 to 11. Again, we switch to the limit of the sum, and again we replace x with a plus delta x times k, and we replace delta x with b minus a over n. Finally, simplifying, we get this expression.
All right, so here is the same thing we saw in that video. We've got our integral. We want to change it to a Riemann sum. We have our height times our width of each rectangle. He used k, we've been using I. If you want to start using j, it's going to be okay. Change the variable up. The change in x is whatever your length is, divided by n. And what you're going to be plugging in, we always have our starting point, which is our a value. That's whatever's at the bottom of your integral, because that's where your area is starting from. And then we see how many changes of x's did we add. We added I of them. We plugged that in for the x, and then we have our change in x there. So our height of our rectangles times by the width of our rectangles. So now, we write each of these as sums. And this, you did this on the papers, but now we're doing it in our notes. So this, and minus 3. Do you see that your change in x, when you go from minus 3 to 3, is going to be 6 over n? We have our starting point at minus 3, and then we take our change in x, 6 over n, I amount of times. That's going to be our x value. And then plugging those things into our sum. So this is the value that you plug in for the x. Our x was x squared, so we have negative 3 plus 6i over n squared times by our change in x. Because your height will be your y value at each of those specific x values that we're plugging in. So same thing in b. Going from 2 and 5 is a distance of 3, so your change in x will be 3 over n. We're starting at 2, so we go 2 plus, right? this part is always a plus change in x times I. That's always that part. You have your starting point and then however many changes of x's that you've included up till I. And then you just plug it into the formula that way. So we have 1 over that. Can you see if they had this on multiple choice and they made a whole bunch kind of look the same? If you had no idea what you were doing, you would have really, really a low chance of getting it right. Hey, you want to try the next two on your own? I'll put the answers up in a second. And I'll put the answers up and you can see how you did. And then we'll end on the next question, but it's a multiple choice. See if you can figure it out. How many people have already got an answer for the multiple choice? Okay. So, did you notice that this distance was 2? So it made me think B and D right away because it had the 2 over N, not A and C. So there's our change in X. The part that gets plugged in needs to be your A value plus your change in X multiplied by some variable. They're using K. Did that throw you off? Are you okay? That wasn't an I? So then your general term looks like this. Which one matches up? It is D. Maybe we have time to do a little bit more. Let's do a little bit more. Now can you work backwards? You've got the sum. Could you write the definite integral? And this is where if they wanted to be a little bit mean on multiple choice on the exam, they could. So we'll see. Because there's like the typical what you would think, and then there's people messing with you what you would think. So maybe we'll see some of those. So here's our sum. We have to figure out what our lower limit would be. And normally what you plug in for the x, so we're sort of supposed to look for an f of x times a change in x. That's the kind of idea that we're looking for, right? So when we're looking at where our x is, right, when you do it in the Riemann sum, your x is always a plus your change of x times I. We're not at, I don't see anything a plus here, right? So it has like a 0 plus. So it makes me think I want to start my lower limit at 0. My change in x is pi over n. Does it make sense that this top number, this pi, is your distance from A to B? If A is 0, does it make sense that your B value is going to be at because we have pi over n is usually b minus a over n, so we would say b value would have to be pi. So this is us working backwards. Notice that if you have your change in x, you can write a plus change in x times k. We see that we have this pi over nk plugged in here. So plugging everything back, you're going to go from 0 to pi of cos of x dx. Where could they get really, like, they can mess things up, is that they play around with translations. So if I took cos of x and shifted it 1 to the right, the area would now be from 1 to pi plus 1. And I would have a cos x plus 1, or x minus 1, inside. And that would still technically be right. It would just look completely different. That's where I said they can be, like, they can be mean. Because the area under cos from 0 to pi stays the same if I move it over, left or right. All right, we'll end there.